Okay, time to get started. No quiz today, as I'm sure you've noticed. So a couple of things I want to talk about. First of all, we are recording right now. For the rest of the semester, we'll be recording the live lectures. We haven't been recording up to now because y'all have already had a video reference, namely the pre-lectures. That's the video reference on the material for the first half of the course. For the second half of the course, due to the absence of those pre-lectures, we're recording the live class meetings. Okay, so one thing to point out, I doubt anyone cares, but just partly for legal reasons, I think I'm required to point out that this is being recorded. Audio from the room is being recorded. It's mostly going to catch my voice, but conceivably, if you ask a question, your voice might get picked up by the mic, so you've been informed. Okay. No more quizzes on pre-lecture materials. However, there are still going to be quizzes. Quizzes at this point will just check attendance, just to confirm that you're here in the room. There's just too many of y'all for me to actually have an attendance roster and go through and check off names. It's just it's not feasible. So this is my little hack for checking attendance. There is a quiz on Sakai, just like there always is. There is a number written on the board every day. There will be a number written on the board every day. That number is the answer to the quiz question. Question just says, what's the number on the board? Or something to that effect. Anyway, you have to take that quiz, enter the number, click submit or however that works, at some point during the lecture. All right. First day here, hopefully maybe for the next few days, I'll kind of remind you if I think about it. Hey, don't forget to take the quiz. Anyway, make sure that you do it. Make sure that you can remember to do it. A couple things about availability. It's available during class time. It's not just the first 5 minutes like the old quizzes on content. So you can do it any time during the lecture. I also open the quiz 5 minutes before lecture starts. So if you want to get here a couple minutes early, tap into Sakai, enter the quiz, get that done first so you can sit back and relax for the rest of the lecture. You've got that option. Also, just in case you might, not get here in time for that and not want to be distracted during the lecture and want to do it after the lecture, you've got 5 minutes after our scheduled class meeting period ends. So 5 minutes before, 5 minutes after. So if I remember correctly, 3:15 to 4:15 will be the schedule for these quizzes. Okay. One last thing. So the content quizzes that we've been having up to now, you could only answer one time. That was necessary to avoid students entering an answer, going to the grade book, seeing if they got the point or not, and then going back and maybe entering another answer for the quiz. So this wouldn't make any sense. At this point, though, since it's just to check that you're physically here, you can take the quiz as many times as you'd like. So if you inadvertently typo or whatever, right? No problem. Just take the quiz again. Just in case it turns out you had it right the first time and you changed it or something, doesn't matter. I've got it set that it will record your highest score. Right? So as long as you go in and see in the grade book that you've got the point recorded, you're all set. Nothing can possibly go wrong. Don't worry. Okay, so everybody how that works? Any questions? Okay, so anyway, in case you haven't already done so, please the quiz answer sometime nowish. Okay, so we are going to spend a few minutes talking about old material. Here is an old exam question. So this relates to the pre-lecture that y'all all watched before this class. And this kind of relates to the this whole business with gain and phase shift that was in the pre-lecture. Really, though, this business about gain and phase shift is just kind of one of the applications. The big math idea in play here is that if you're interested in solving a differential equation, say like this, right, then you can make the associated complex equation like this, and because the real part of that is that,
turns out, as we argued in detail, and I won't go through that argument again, that the real part of that is that. So said differently, if you solve the complex equation, then for free, you get solutions to the real equation. And likewise, the imaginary equation at the same time. Okay. All right. So that's what this question here is about. You'll notice the first part of this question says, solve this differential equation. It's what it is what you might say an associated complex equation. And we're going to go through and talk about how to do that solution. But notice that having done that, next part of the question says, solve that equation and solve that equation. And rather than doing these individually, with sines and cosines in each one and having just, massive trig all over the place, and then a system of equations where we'd have to solve a 2x2 system for the A and the B, both of these just kind of drop in our laps. So anyway, let's not get too far ahead of ourselves. Here we go with the first part of the problem. We have a right-hand side, as we've done in multiple instances back in section 4.3. Our guess is going to be pretty much what you get from looking at the right-hand side and then thinking about what other kinds of terms might show up in the process of differentiating, as the left-hand side does. Beautifully, it's just an exponential, and so when you take derivatives of exponentials, only exponentials show up. So our guess is just a scalar multiple of our right-hand side. There's our scalar multiple, and you take this guess, pop it into there. The differential equation becomes this. Do notice I had to take some derivatives. I had to take this z function, and I had to take a derivative. I had to take a second derivative. So that kicks out some extra scalars. We're going to keep track of those. But having done that, notice that the common factor of e to the 2it cancels. Conveniently, this 7 cancels. That's nice. All that disappears, and all that we're left with is this. And solving for t is simple complex algebra. Right, so. Now, admittedly, you do have to do a complex division, and there is that one little trick there, right? Remember, you have to multiply and divide by the conjugate of the denominator. No big deal. A little bit of arithmetic, but... Okay. Now that we've solved for t, that goes there. And our actual solution, then, this z, is that, and now you'll notice this number right there, and let's see here, orange, e to the 2it there. So you plug in the t, and we're pretty much done at this point. Now there is something awkward about this solution, the way this is written. We've got a complex valued number times a complex valued function. That's weird. It's not clear how to deal with this. It's this number as it's written. This is not in polar form. It's not in rectangular form. It's just kind of neither. This is just a mess. Right? So we do have to simplify this. We have to multiply this factor times that factor. Now, you can go about this multiple different ways. I think the easiest way to do this is to put both of these factors into rectangular form. Put them both in the rectangular form and then just FOIL it out. Whoops, let's see here. Purple. So, notice all I did here is put that into rectangular form. And here's the foiling. So, real times real. Imaginary times imaginary. Both of those give you real products. And then, going the other way, real times imaginary, and imaginary times real. Straight up FOIL. No tricky curves really on how that arithmetic works out. How we doing? Is everybody happy? Any questions so far? Is good? Okay. By the way, a quick reminder. You may recall when we were talking about section 4.3, one of the questions, there was a long list of old exam questions from 4.3. One of them I skipped over, and I said, well, let's not do that one just yet. It's going to make more sense in a different context. This is that old question that we skipped over at the time. What we hadn't seen at that time was the idea of a complex right-hand side and a complex solution, and certainly we hadn't seen the idea of using complex solutions with complex right-hand sides to solve two separate differential equations, like we did in today's pre-lectures. So I felt like it would just make more sense to wait. So here we are, and but notice, even though, we did use this whole business about complex this and that, this is morally just a 4.3 problem. Right? This is just, make a reasonable guess of what your form is, plug it in, and then solve for your fudge factors, your undetermined coefficients. T, in this case. Okay. All right. Okay, so now again, we're well set up to answer the remaining two questions. This differential equation by itself would have been a kind of a bummer if we were to do it separately and without any complex, tricks. But here, I can just say, well, look, this is the real part of the right-hand side that I just got through solving the differential equation for. And so, what I'm interested in is just this real part of that. The real part of the z I just solved for above. Done. How are we doing? Let's see what happened there. And likewise, for the other side, this is the imaginary part of the z that, of the right-hand side that I just got through dealing with. And so, as such, the right-hand side here is the solution that I'm looking for. So, same idea that we used in the gain and phase shift business. Different application here. Here I'm not actually looking for a gain or a phase shift, but the big math idea of taking a real differential equation and sort of choosing to alternatively look at a seemingly harder, but in fact easier, complex differential equation instead makes your life easier. Alrighty. Okay, so that's all I've got for the rest of Chapter 4 there. So we are now done with Chapter 4. We're going to move on now to Chapter 5. First, a little discussion of, sort of where we are in the course structure. Remember, the very first thing that we did in this course, the first quite a few weeks, I've lost track of where we are exactly right now, the first 5 or 6 weeks of the course, was linear algebra. Spent a bunch of time doing linear algebra, systems of equations, matrix multiplication, determinants, linear independence and span, dimension, vector spaces, subspaces, all that kind of business. All linear algebra. Now, why did we do that linear algebra before the next section of the course, which was differential equations? How come we didn't just start with the differential equations? Well, very good reason. In order to be able to solve those differential equations, we needed all of those ideas developed. Right? Look at the way we solved those differential equations. A big part of solving those differential equations was understanding homogeneous solutions as a vector space. Understanding that they can all be viewed as in the span of a basis, that basis being a fundamental set of solutions. Right? So we have all these linear algebra tools that went into understanding what the solutions were. By the way, how did we know we were done? How did we know we found all of the solutions to the differential equation? Well, by way of a dimension argument. Right? We knew that the dimension had to be exactly n, and so we knew we needed to find n linearly independent solutions. Right? So that idea of dimension that we developed in Chapter 2 is a necessity in a full discussion of the differential equations in Chapter 4. Okay, so the big pattern then is linear algebra followed by a bunch of differential equations that require using that linear algebra. Okay. So we are now about to shift over to the sort of second half, you might say, of the course, in the sense that we are now about to do a bunch more linear algebra, followed by a bunch of differential equations whose solutions will require the use of that new linear algebra. Right? So it's a nice course structure, I think. There's a bunch of linear algebra we have to develop, quite a bit. It's going to take us a while to get there. Right? So there are many applications coming of what we're about to start talking about, and all the stuff we're going to do here in Chapter 5 and then subsequently in Chapter 9. But it just takes a long time to get there, so anyway, bear with me. Thank you for your patience. I'm going to move on now to talk a little bit about functions. This is just to get our terminology straight, make sure everybody's using the words properly. So, describe a function. Very often people mistakenly think that a function is just a formula. It's not really quite true. A function is really a trio of things. A function is a formula that you typically get a name to, like let's say f. This thing called the domain. The domain is the set from which inputs to the function come. And then finally, a set called the target. And the target is the set that outputs from the function have to land in. So, inputs to the function come from the domain, outputs from the function land in the target. So really a function is the trio of these things. It's the formula for how to get an input into an output, but also what is the set of allowable inputs and what is the world that the targets are required to land in. Okay, another little bit of terminology. There are other words that target sometimes is referred to as codomain. It's also sometimes called the range. I'm going to have to put an asterisk on that. I do have a discomfort with the use of that term range, and I'll tell you why in a couple seconds. Okay, so I want to describe now another set that's involved in this picture. It's called the image. The image is the set of actual outputs. Now, a lot of people will look at the image and think, "Oh, come on, it's the same as the target. It's the outputs, right? That's what the Y, the target is. That's what it's the outputs, right? It's just the output. The image is it's the outputs. What's the difference? So there's a subtle but important difference. The outputs are all required to be in the target. The image is the actual set of the outputs themselves. So, the thing is, they don't have to be the same set. The image is required to be a subset of the target, like all the outputs. The image is a set of actual outputs. All the outputs have to be in the target, therefore B is a subset of Y, but not necessarily the other way around. There could totally be points over here that are in the target, but they're not in the image. Okay. Alright, so they're not the same thing. You would think that the image is the more interesting of these two things. After all, the image is the actual, the tight set of actual outputs, sort of no extra, sort of sloppy flab on the sides here. As it turns out, the target is really the more interesting thing to talk about. And I'm going to show you an example of how that comes about in just a moment. Okay, first an example of the difference. So let's look at this function here, function from R1 to R1 defined by this formula. Notice we have a domain, we have a target, and we have a formula. Right, so this is the trio that defines that function. All right, now with that noted, The target is R1. The image is not. Right? The image, the actual outputs. If you put in a bunch of all possible real numbers and put them into this formula and ask what comes out, well, only non-negative real numbers come out. Right? Give me 2 seconds. So these are not the same set. There's nothing you can put it. There's no real number. Keep in mind our domain is R1. There's no real number that you can put into this formula and make a negative number come out. R1 has negative numbers in it. This image does not. Yeah.
So then that's like a function that multiple targets then?
I know what you're trying to say. Let me say that a little bit differently. I can define a function with a formula that has a certain target. You can then define a different function that has the same formula and the same domain but a different target. Right? But the point is they are then different functions. So keep in mind the function is the trio. The function is all of this together. And if you change anything that I've got circled in red here, now you've defined a new, different function. Yeah. But let me say it a little bit differently then. If you have a formula, then you can use this formula and change the domain, change the target. As long as everything in the domain goes in, and as long as everything that comes out from the target, cool. And you've got a lot of options. Sure. Okay. Anybody else? Okay, another example. Let's look at this function. Got a domain that's R2. By the way, you can see that the domain is R2 because what goes into this function is an ordered pair, and furthermore, any ordered pair is fine. Whatever element of R2 you pick, no issues. I'd be plugging Tug into this formula. I'm not taking log of anything that might not be defined. I'm not taking a reciprocal that might blow up or anything like that. No problem at all. R2 is the domain. I'm going to say R1 is the target. Do notice that what comes out, the rules about the target, everything that comes out must be in the target. And that's true in this case. Everything that comes out is a real number. And that's fine. But not every real number comes out. This is another example of a function where the image is not the same as the target. The image in this case is, let's think about what values could this expression actually take. Well, it can get arbitrarily large. We've got, highest order terms of 4th powers. But putting in large values of x, large values of y, you can get as big as you want. Right? But it cannot get arbitrarily small. There is a smallest that this function could get. If you were to draw a graph of this thing, it would be like a kind of paraboloid-esque, and it would have some sort of a lumpy shaped bottom, but it would not go down. So there's going to be some minimum value. The image is going to be all real numbers greater than or equal to something. And here's the problem. Here's why I don't like images. I don't know what that something is. And maybe I don't care. Right? If I want to talk about this function, maybe this function describes something I'm interested in, and I need to know its values at certain places. I need to know maybe its partial derivatives in certain directions. What have you. I don't need to know its minimum. I don't want to be responsible for finding its minimum. I can't write down the image of this thing without dealing with a nasty optimization problem. Got the nasty problem. How do you find that minimum value? You take the gradient, you set it to the 0. Gradient, qubits. Q. This is a very, very hard function to optimize. And I don't want to deal with it. So, very often stuff like this happens where finding the image is just very inconvenient and entirely irrelevant to what you're looking at. Okay. All right. Pause for questions. Everybody happy? Okay, so that's the terminology we're going to use. So let me come back to one thing here now. Why don't I like this word range as a synonym for target? And the reason why is tragically, I have seen the word range used as a synonym for image. And that's unacceptably confusing, right? You can't have... It sort of defeats the purpose of a word, if that word might mean two importantly different things. Okay? So I just feel like this word, because it's been used in different contexts. By the way, very often, this word range is conflated between these two things because plenty of users don't really appreciate how target and image are in fact different. Right? And if you don't see the importance of the difference, then why would you distinguish between them and you use one word to represent, well, who cares? Right? So that's my theory. That's what's happened. But the word is problematic as a result. So if you hear people talking about the range of a function, your ears should perk up and you should think, oh, what does this person think the word range means? And whatever, it's just a word, but make sure to realize what they intended to say before you possibly might infer incorrectly. Okay, moving along. So we're going to finally make a definition. Now this is a big relief for me. I've been biting my tongue all the way through this course. Things called linear transformations have come up in several places in this course. I couldn't use the word linear transformation because the book hadn't defined it yet, and I didn't want to get ahead of us. But here we go. We're going to define this thing called a linear transformation. It's not that big of a deal. A linear transformation is just a function whose domain is a vector space, whose target also a vector space, and which satisfies this property here called the linearity property. Y'all will recognize this property. We've used this property in multiple previous contexts. This is just the idea that if you put a linear combination of vectors into the function, you get the corresponding linear combination out of the function. Right? But there are several different contexts that we've used this so far. So, any such function is called a linear transformation, and now I don't have to bite my tongue anymore, and when we encounter a linear transformation, I can just say linear transformation. Okay. Questions on the definition? Everybody see what we're talking about here? We're going to see a bunch of examples coming up here. Some today, some on Wednesday. Even more on Wednesday. Okay. This linearity condition. It's not immediately obvious, but it does turn out to be true that condition is equivalent to this condition. A little surprising at a glance. This top condition says that this linear combinations requirement has to work when you have linear combinations of two vectors. This one down here says, and further, it has to work with any finite linear combination of vectors. This seems like a stronger condition. Turns out that they're identical, so any function that satisfies this top condition has to also satisfy the bottom condition, and vice versa. Proving that is just a matter of repeated application of this top condition. So it's not a hard proof. If you're curious, if you'd like to see how that would be written down, come talk to me in office hours. Ask your TA in office hours. Ask any of the TAs. Of course, reminder, you're all invited to all of the office hours of all of the TAs. A third alternative way to write this is this one down here. This is actually two conditions. Adding the vectors that go in, add the values of the function, comma, furthermore, scalar multiplying an input, scalar multiplies the output. So any function that satisfies these two conditions must also satisfy that condition. Must also satisfy that condition up there. So the three things that I have circled in purple are all equivalent. So that's equivalent to that, and that's equivalent to that. And etc. Take your pick. Different linear algebra books will make different choices about which one of these to make the definition. It's been a long time, but I think I remember from when I was y'all's age. I think the book that I learned from used this as the definition. It doesn't matter. It's equivalent to this. It's equivalent to that. Okay. All right. In this course, we're using that as the condition. One nice thing about that condition up there is it's only one condition. Write this down here. It's two separate requirements. If you're doing a proof, if you're trying to confirm something, the linear transformation, you have two separate calculations to do if you use this definition down here. So that's only one condition to check, and furthermore, it's a relatively short list of only two vectors to deal with. So you don't have to deal with the additional ... in here, and you don't have to deal with the fact that there's two conditions here. But feel free to use any of these at any time. Okay. All right, a little bit of lingo. This is nice. This condition here is sometimes referred to as saying that the function commutes with linear combinations. I hope y'all remember this word commutes. Right? In different contexts, maybe when I was in elementary school, they talked about the commutative property of addition. I've never understood why they don't memorize that these words that describe the trivial, obvious property of real number addition. That A plus B equals B plus A. My gosh, of course it is. Why are we talking about this? Like, little did I know that was going to be a big deal in math. 216. Anyway, so commutes in some sense means that you can change the order and it doesn't matter. You get the same answer no matter which order you go in. So that's kind of what's happening here. Now, of course, these aren't real numbers that are being added. This is, I guess you might say processes that you're doing in different orders. You can do a linear combination and then apply the function, or you can apply the function and then do the linear combination, and you get the same thing either way. Right, so it's still, cosmetically, it's still got that kind of switch the order, who cares, kind of a vibe to it, even though it's not technically quite the same thing. But this makes for a very easy way to describe that property. We say that the function commutes with linear combinations. Very succinct way to describe that property. A very common usage, so you're going to hear this a lot. This is what people mean when they say a function commutes with linear combination. Pause for questions. Everybody on board? All right. Okay. Equivalently, this is what people mean when they say it commutes with addition and commutes with scalar multiplication. Commutes with addition means that. Commutes with scalar multiplication means that. Same idea. Okay. All right. Okay, a little bit of lingo. We try to be as precise as possible when we're doing math. However, when it's clear what the interpretation is, sometimes mathematicians like to use what I like to call math slang. So I'm going to show you some examples of kind of math slang. The moral, the upshot, the interpretation of all the examples I'm about to show you here is how people will sometimes talk about linear transformations without actually coming out quite and saying linear transformation. In fact, without even coming out and really describing what they're talking about as even being a function. And yet what they're saying is, hey, this is a linear transformation. So, for example, left multiplication by a matrix. People will say the matrix acts linearly on vectors by left multiplication. But you'll hear it as tersely as a matrix acts linearly. Okay. So, when you see this word linearly or linear, you should draw two conclusions. Somewhere in the conversation, somewhere in the discussion, what the speaker is talking about, there is a function. Right? Now, the speaker here has not said, I hereby define the following function. Right? But they're implicitly suggesting that, look, this thing that I'm talking about is a function. So make sure to identify what is this function that they're talking about, even though they didn't technically say it. Secondly, the second inference that you should note is that function that they were talking about is a linear transformation. Okay, so let's do that here. What is the function? What is it that matrices do? Well, if you give me a vector, here's what matrices do. All right, I've got a vector, and then someone says, "Hey, here's a matrix. Do something with these." Well, all I can do is multiply the matrix times the vector, like this. And this is the action of a function. In fact, we've written this function down before. We've written down before t of x equals ax. Right? This is our interpretation of a matrix as a function. The function is called t. If you give me an input x, I give you as my output a times x. Okay, so that's the function. And so when the speaker says a acts linearly, this is the function that they're talking about, and by saying acts linearly, they're saying that this function is a linear transformation. Right? So it's just a very terse and convenient way to talk. It's just a lot easier to say matrices act linearly as opposed to the alternative, which would be I can interpret a matrix as a function, and that function is a linear transformation. It's just a lot more syllables, and it's just easier to... Anyway, you're going to hear a lot of this. By the way, the reason I mentioned this example, and the several examples that follow, is that the Math 353 instructors, y'all are all going to be taking Math 353, the vast majority of y'all will be taking Math 353 very soon, and they've commented that they're kind of surprised that students seem to not know what they're talking about when they say this. Right? So the instructor says, okay, we've got a matrix and it acts linearly, and then blah, 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 blah. And apparently a lot of students get to Math 353 not being able to sort of, interpret this, like I say, slang language. So I just want y'all to be heads up about this. If you see the word linearly, realize that the speaker is speaking a little casually. They're describing that there is a certain function, and they're asserting that that function is a linear transformation. All right, here's a couple more examples. Suppose you have a plane. Let's see, you have a plane P. Oh, hang on. You have a plane P here, and let's talk about projection into that plane. Right, so if you give me a point, you give me a point x, I can talk about projecting that point x into the plane, and the result is, well, whatever this, nearest point in the plane to x. Okay, so different versions of how people might sort of say this, but a pretty common way for someone to talk about what's happening here is to say projection is linear. Right? Okay, well, let's look at that phrase. Projection is linear. There's that key word, linear. This speaker is describing something to do with a function. What is the function that's in play here? Well, the action is that we started with some point x and we ended with some point here in the plane P, the one that's the closest to the original point x. So that's our function. Right? And the assertion that the speaker is making here is that this function is a linear transformation. Okay. Everybody see what happened there? So again, you could say we define a function t by t of x equals the point in the plane P that is closest to the original point x, semicolon, that function is a linear transformation. Right? But it's just a lot easier to say projection is linear. Okay. All right. Okay, here's another example. We've talked about this thing in the past. I haven't used this notation yet. We'll come back and talk about that notation in a moment. But we've talked about this process. This is what we've previously called L. We've talked about L of F. Right? Chapter 4. Shorthand to represent what happens on the left-hand side of the differential equation. You give me some function f or y, whatever. Give me some function, and the left-hand side of the differential equation says, look, take various derivatives multiplied by various coefficient functions, and the result will be a function of x. So we've made the interpretation that that is it's a kind of a function. You give me an input, I give you an output. The input that you give me is a function f. The output that I return to you is another function, and here's the formula of how it's computed. Now, at the time, in Chapter 4, we called this an operator. We called it an operator because this is one of those weird kinds of functions that takes as its input other functions. Right? And that's a little confusing, so we give a different kind of a name to the what you might call the outside function, the one that, the L in this case. Call it an operator to distinguish certain. Operator refers to this thing, function refers to that thing. Right? But nevertheless, this L thing, this operator is a function. So when this is described as a linear operator, let's follow our rules. We see that word linear, which thinks, okay, step 1, where's the function? There's a function in the story here somewhere. Where's the function? The function is this thing L. Step 2, interpret that the speaker is telling me, by their use of the word linear, that that function is a linear transformation. So, this thing is a linear operator is code for this operator could be thought of as a function which I can show as a linear transformation. Just more awkward to say, more syllables. Last, going back to the very first thing we talked about in this course, we talked about systems of differential equations. Systems of linear equations like that. So we called them linear systems of equations. There's that word linear. Why do we call these linear? Okay, find the function. Somewhere in this story of the systems that we considered in Chapter 1, there is a function. And the function is this. It's this thing right here. If you give me a set of inputs, x1 through xn, I give you an output, namely the whole left side of the system. Right? We've written this as a function before, in fact. Let me just remind you. You can rewrite this input as x, and this output is t of x. Right? I mean, certainly this output is ax, and remember we've represented ax as t of x in the past. So there's the function. That's our function. When we say we have a linear system of equations, what we're saying is that I can interpret the left-hand side of the system as being the action of a function, and that function is a linear transformation. So, which by the way it is, and which is why it's reasonable to call this a linear system of equations. Okay. Alrighty. Okay, moving along. We're going to have to get our hands dirty. For one, everybody should do at least one of these in their lives. This one's your turn. You might have to do another couple here or there with some homework exercises, maybe even an exam question. But anyway, here we go. We're going to look at this function here. Right, we're going to try to decide, is that a linear transformation? Okay. Quick observation, the domain is R2. It's clearly a vector space. The target, R2, clearly a vector space. No issues there. What we need to do is check and confirm that this formula satisfies the linearity condition. There's just a bunch of algebra to do here, and we're going to wade our way through it. Let's see here. Let me space this out. Notice what I've done in this calculation. We're going to go through it all, but just big picture. notice that I've showed that this function commutes with linear combinations. Linear combination before the function, linear combination after the function. Said differently, linear combination of the inputs yields the same linear combination of the outputs, whichever way you prefer to think. So all this calculation that we're about to walk through, the purpose of that is just to confirm that we've satisfied the linearity condition. And here we go. Deep breath. Looking at our starting point. I need to plug into this function t. The formula that I have for t requires that I know the coordinates of this input vector. So this thing here, I need to understand it in coordinates. So let me rewrite it in coordinates. Notice I've just given coordinate names to the first vector x1, and then now I've given coordinate names to the second vector x2. It's just making a notational choice about names. Math 212. Multiply out those vectors. Multiply, collect terms, usual way. Nothing tricky there. Okay, now I have my input in coordinates, right? I've got my, the first coordinate of my input vector is, well, that thing. My second coordinate of my input vector I see now is that thing. And so all I've done here is take my formula for t and rewrite it by plugging in. Right, so this x, that formula for x, it goes there and there, namely there and there. The formula for y, this here is my second coordinate of my input vector, that goes there and there, namely there and there. So I emphasize I didn't really do anything here yet. Right, I'm just plugging in. This says t of that thing, and I'll say, well, that's what this is. Okay. How do we proceed? Let's cheat a little bit. Notice where my goal is. My goal is to get down to a times something, and then b times something. Right? So, said differently, I need to get sort of all my terms that have a in them over kind of on the left-hand side, and I need to get all my terms that have b in them sort of over on the right-hand side. So, that's all I'm going to do in this next step. I'm going to observe that these are the terms that have a's in them, and I'm going to just move them all over to here. These are my terms that have b's in them, and I'm just going to move them all over to here. And move parentheses around, factor out the a's, factor out the b's. Observe that this is exactly t of x1, this is exactly t of x2, and we're done. So it's, these brute force proofs of linearity is just a matter of taking a deep breath, plugging in the left side of the linearity condition, and compute, rearrange, and observe that it does what it's supposed to do. Okay, so this makes for a good stopping point. See y'all later. Have a good Monday. See you on Wednesday. Don't forget to do the attendance quiz right here. Make sure you got 5 more minutes before that's over.